Hello, everyone. My name is Marjan Verhelst. I'm a professor at the University of Leuven, KU Leuven, and I'm also a research director at IMEC. What I want to talk to you about today is on how we can enable running deep neural networks at extreme edge devices. Extreme edge devices being things like my phone, my wearables, implantables, basically all kinds of devices that are very, very resource constrained. Yet, we want to make them smart and embed machine learning in them. This is a trend we see more and more also at the ISSCC conference, where I am a subcom chair of the machine learning subcommittee. And also recently we started a new initiative called TinyML that groups people with a growing interest into such smart extreme edge devices. You would maybe think that today we already have this. We have smart devices, like our phones can recognize our faces. My phone can do speech recognition. I get more and more smart cars, self-driving cars are getting closer and closer. And there is new applications using smart glasses. So you would think deep neural networks or machine learning in general is already everywhere in our edge devices. Yet, question is, are they really? Because yes, my phone can recognize my face, but it can basically only do very simple recognition tasks, like a face recognition, or yes, it can detect speech, but only certain keywords. Running full speech processing is something that's still mostly done in the cloud. And also smart cars are maybe creeping closer every day, but it's going very slow because at the moment, the processing in a car is still very, very power limited. Behind the glove compartment of a car, I can shuffle a chip that can run up to 10 watts, but that's not enough to realize the smart or the algorithm that we need for smart driving. And also smart glasses exist, yes, but either they're very, very bulky with humongous batteries, or they have very limited functionality. So no, we do not have truly intelligent edge devices so far. Why is this? What is limiting us and where is the state of the art? Well, let's do some back of the envelope calculations. For example, on the left, I have my smart car application, and assume very, very naively that I have 6 cameras, like HD cameras, that they have to run at 30 frames per second, and I do a ResNet 50 network on each of my cameras. I know that ResNet 50 is for sure not powerful enough to be able to support self-driving applications, so it's an underestimation, but it's just a back of the envelope calculation. If you would make this assumption, you would have to have compute power to run 300 giga operations per frame, or about 100 tera operations per second. And to fit this in a 10-watt power budget, you need an efficiency of about 10 tera operations per second per watt. Let's then look at a second application, very different one, and my smart glass application. This one has a much lower power budget. It can only consume about 100 milliwatts, when it's always on. But of course, it also has less cameras. And if you do the math here, you'll see that I only need about 10 tera operations per second, but at a much higher energy efficiency of about 100 tera operations per second per watt. Is this feasible nowadays? Let's take a look. First of all, it's definitely going to be a matter of both throughput and energy efficiency. Throughput meaning that I have to meet with my compute platform a certain target time per inference. I have to meet my real-time deadlines of when I have to process the next frame. And on the other hand, energy efficiency, I have to be able to do my inference with a certain amount of energy, either limited by the cooling of my chips or by the battery power I have available. If we now take a look at these two applications and map them in this plane, so on the horizontal axis, I have my power consumption expressed in watt. On the vertical axis, I have my throughput expressed in giga operations per second. And I map here both my smart glass and my smart car application, and with the specs that we just derived, yes, these naive, underestimated workload specs. Let's see what the state of the art can do today. First of all, we can think of using GPUs. Embedded GPUs or more powerful GPUs You see a variety of them here that you can buy today. And what you can clearly see is that yes, they can get the throughput specs I need, but not at the efficiency metrics that I care about. By the way, on the horizontal axis, you see my power consumption, but these diagonal lines basically combine my throughput and my power consumption specs in terms of energy and give me an energy efficiency spec at these tera operations per second per watt. You see, GPUs, though they can get the throughput that I need, they do not get sufficient energy efficiency, definitely not for my smart glass applications, but also not for my smart car application. Of course, more and more people start to not just use GPUs for these kind of applications, but they build customized processors. And then, for example, map these customized processors on FPGAs. What you see here is the efficiencies and throughput that people were able to achieve with such custom neural network processors on FPGAs. And you see, it doesn't help that much. And yes, you can get a more efficient architecture with some custom FPGA design, but the FPGA platform itself is not the most efficient platform. So it doesn't bring us much further. Of course, the next step is to take these custom architectures and map them on ASICs, so custom chips. And then you see the design space again opens up much more, and you do get better energy and power efficiencies from this. So you could say, hey, this is interesting. It seems to be that there start to be designs and products here that get very close, if not even reach, these targets I had for my two emerging applications. How do they do this? Well, you will see in this presentation that it's a battle on many fronts. On one hand, yes, people are making custom chips, more efficient chips that push the tera operations per second I can get out of my running my workloads, and also the tera operations per second per watt, my energy efficiency metric here. On the other hand, there are also people that are not working on the chips or the hardware implementations themselves, but they're really pushing the algorithms. They're trying to get algorithms that get the same accuracies, the same application level performance metrics, but requiring less operations, making neural networks that are more compact and elegant to run the same tasks. They are constantly pushing down the operations per inference without hurting accuracy. And then you have this whole group of people that says, okay, you can have better chips and good algorithms, but you especially need a good mapper, a good compiler that takes the algorithm, maps it on the chip as efficiently as possible. Basically, these guys are pushing the utilization of the hardware for a given workload. So can I keep my hardware as busy as possible with these algorithms? Now, obviously, if you try to push this throughput, this energy efficiency we talked about, you have to innovate, or you can innovate at each of these fronts. Because my time per inference is obviously a combination of how many operations I have to do for my inference, times how efficiently can I map these operations on the hardware, times how efficient is my hardware. And the same holds for my energy per inference. It's my hardware efficiency, my mapping efficiency, and my algorithmic efficiency. So people are fighting on each of these fronts, often in their silos. So people fighting on making better chips, making better mappers and hardware architectures, people getting better algorithms, all trying to shoot and maximize their performance metric at their level. So let's try to see what's happening at each of these levels. What are the big trends here, and what should we be careful for? And I'll start with the circuit level. So at the circuit level, it all boils down to making as efficient as possible multiply accumulate structures. We also will call this a MAC. A MAC is a multiply accumulate hardware block, and this is going to be of prime importance at the lower design levels of your neural network processors. To understand why this is the case, let's briefly take a recap of these kind of machine learning workloads we're interested in. I will focus here on neural networks, and especially, because they're very common, on convolutional neural networks. Such convolutional neural networks basically consists out of layers of the following structures, where every layer will take an input, a three-dimensional input tensor, takes out small parts of it step by step, and is gonna multiply or convolve them with some weight kernels. Such a convolution is basically a multiplication, element by element, followed by an accumulation. This results in one specific output value. And I repeat this operation now by shifting this blue part across my whole input region. And this will give me output pixels across the whole output region here in 2 dimensions. To get the other k different output planes, I will repeat this whole operation with k different green kernels. So what you basically do is you do the same operations over and over again to get many different outputs. And every time you have to do many multiplications, many accumulations. So at the lowest level, it boils down to doing such a multiply, accumulate as efficiently as possible. Custom hardware architectures for neural network processing hence typically boil down to having a data path with a sea of processing elements that contain such multiply, accumulate blocks, and some register to constantly feed them with data. And this data then comes from a more or less complex memory hierarchy consisting of SRAM and register file buffers that are again fed in their turn by external DRAM. So at the lowest level, people try to optimize performance here by making this multiply accumulate block more and more efficient. And one of the most prominent trends here over the last few years has been to play with the precision or the data type at which we compute in these multiply accumulate blocks. Starting from floating point, people quickly went to 16-bit operation, 8-bit fixed point operation, and even lower precision. And here you see that you can do a 4x4-bit multiplication or even do asymmetric precisions, where you maybe use more bits for the activations and your inputs, but less bits for the weight kernels. All of this has been played with a lot because it has a humongous impact, but the downside of going to lower precision is obviously that now you're stuck at this low precision. Maybe some networks run perfect at 4 bits, but other networks still need 8-bit or 16-bit compute. What to do? So this is another trend that starts to appear in almost every deep learning chip, is that we don't design for one fixed low precision multiply accumulate block, but we try to make multiply accumulate blocks that can dynamically change their precision, that can work in 8 or 16-bit modes like you see here, but that can dynamically downscale their precision to 4-bit operation, 2-bit operation, and so on. And of course, if they go to lower precision, you try to get some throughput in return by using more and more parallelism. This is an example of how we did this in our design in 2017. More recently, people have shown other ways to make such precision scalable multiply accumulate blocks, and like Bitfusion in 2018, or many different other techniques later over the past couple of years. And what you can see is you can implement this in different ways, but it's very hard to compare them because they were all implemented in different technologies and different design flows. So what we did in our lab is we took all these different precision scalability architectures and we implemented them in the same way, in the same technology. Some results of that you can see here. So again, on the x-axis, I have the throughput. This is now expressed in terms of throughput per millimeter square, normalized. On the y-axis, I have the energy efficiency. First of all, the red line here on the top is when I have my baseline design that is not precision scalable. In our case, we started from an 8-bit multiply accumulate unit as the baseline. You could as well have started from 16-bit. And all the lines here in the bottom are the precision scalable multiply accumulate units when they run in 2-bit mode, so at a 4x lower precision. What you can see is it depends a bit on in which way you impact or implement this precision scalability, but definitely you can save a lot by making your design precision scalable and get up to a 10x energy efficiency boost from going to lower precision when necessary and a 5x throughput boost without having to give up your capability to run in a high precision mode at 8-bit or even 16-bit if you want. Of course, let's see again what this brings us in this overall overview where we started from. What I did now is I color-coded all the ASIC designs, so the custom chip designs, with the precision at which they run. So these triangles you see here, they represent what fixed point precision they run at. And you see here you have some 16-bit fixed point implementations. When you go here, and especially looking at the cyan triangles here, these are all 8-bit solutions, getting some better energy efficiency. Going to the pink ones here, these are 4-bit solutions, again, 4-bit fixed point, getting some more precision, and then some 2-bit solutions here, even more efficient. So going to lower precision helps 1 up to 2 orders of magnitude in efficiency. If you want to push even further, you see with the squares here that people push these even further. Don't compute in 8-bit, 4-bit, or 2-bit, but just compute binary or ternary. What does this mean? Well, it means that I will just make my weights and my activation to be 1-bit signals, and my multiplier then just becomes an XOR. Super, super cheap. My accumulator becomes a pop counter, which is also very simple. And then I do a threshold to get again a 1-bit output. So I go to 1-bit multiply accumulate units, which are efficient in the digital domain. But it turns out you can do even more tricks with them. Because if my hardware is so simple, I don't even have to compute in the digital anymore. I could even try to compute it in the analog domain or the mixed signal domain. And this is something we tried together with Boris Merman, professor at Stanford University, where we took the same structure that we implemented in digital, and now it was implemented in the mixed signal domain as follows. The multipliers are still here. These are these XOR gates, but the accumulation is now done in the charge domain, as you see here. And this, as I will show next, gives a pretty good efficiency boost, energy efficiency boost. But this is not the end. More and more people are taking this analog compute even one step further and start to compute inside SRAM memories in very similar ways. Where now my multiplier is no longer an XOR gate, but I multiply using the SRAM cell. Basically, I store one of the inputs of the multiplication in the SRAM cell. And with the other input, I will either activate or not activate this work line. And the result is that my bit line here will get a charge depending on whether the input here is 1 and this input is 1, and hence kind of gives me a multiplication effect towards charge injection on this word line here. And if I now do this for all these rows of the memory in parallel, then this bit line will accumulate the result of all these simple multiplications. And I get basically multiply, accumulate inside a pretty regular SRAM structure. We call this in-memory compute. Again, does all of this help? Yes. So again, here you see on the x-axis the energy efficiency, on the y-axis my throughput efficiency at operations per second per millimeter square, and all the black dots, they are fully digital solutions. The green dot is this analog implementation from Stanford that you saw in the middle. And what you can clearly see is that this gives a humongous energy efficiency improvement, up to 10 to 100x. Not a throughput improvement because this analog design wasn't more compact in area. But if I go from this analog compute now to the in-memory compute, then you see that this gives you a more compact design because it's in the memory array. And so again, a big boost now in throughput per millimeter square. And then going to our overview, I made all the digital implementations now gray. So these are all these gray items. And I added in color analog and in-memory compute solutions. And you see this again gives us a push in energy efficiency. So you would think, yes, this low precision, even analog solutions are really pushing our efficiency to close to or even surpassing the needs of our emerging applications that we started from. So you could say problem solved. Here I am, I can embed neural networks in embedded devices. But is this true? The thing is, there is a big problem in our reasoning here, because we only looked at it from the circuit technology level. Yes, we were able to push tops and tops per watt tremendously by reducing precision, by going to analog or in-memory compute. But what we didn't realize is that it has a quite significant impact at the architecture mapping level and at the algorithmic task level. You might be doing well here, but hurting these other guys. Let's take a look to these levels to understand that better. And I'll start by the architecture level. At this architecture and mapping level, the goal is to keep my processing array here, my multiply accumulate units I have, to keep them as busy as I possibly can, to maximize the utilization of these processing blocks. How do I do that? On one hand, by making a very, very good memory hierarchy. So I'm going to play with the topology and the number of levels of my memory hierarchy to basically make sure the data path gets fed all the data it needs and there is never a need to stall, or as little as possible. On the other hand, at this level or this architecture optimization, I will have to play with the data flow in my data path. I will try to make sure that every time I fetch data from this memory hierarchy, I use it as efficiently as possible. And I reuse the same data as much as I can. To explain that, let me show you an architecture of a data path of a chip we made, and it's very similar to the later Tesla full self-driving chip, where you have a sea of multiply accumulate blocks, 16 rows and 16 columns of multiply accumulators, 256 max in total. And what we did is, every weight that is fetched is reused across 16 different inputs. So I fetch the weight once and I use it 16 times in parallel. Every input I fetch is reused across 16 different output channels, K. So I fetch the input once and I use it in 16 multipliers together. So you see, by doing this, I reuse the data. I have to fetch my input 16 times less from memory. I relieve the memory hierarchy here. This saves a lot. And you do this by parallelization, as spatial unrolling. In this case, I spatially unrolled over the input dimension X and over my number of output channels K. But it's not the only spatial unrolling I could do. Because, for example, if you look at the Google TPU, it also spatially unrolls over the dimension K, but it spatially unrolls over the input channel C instead of this X parameter. If you look at the Huawei DaVinci chip, it even spatially unrolls over 3 dimensions. So again, a different processing element array topology. And you can wonder which one is the best. How do you know what data flow to take, what memory hierarchy to take? Well, let's first of all see whether this matters. What you see here is the energy per inference for a specific neural network layer for different memory hierarchies. So hierarchy 1, 2, 3, and 4. And for different spatial unrollings. And the lowest one is, for example, the Google TPU. The upper one is our chip or the Tesla full self-driving chip. And these are some other spatial unrollings you can think of. You see, first of all, the difference in energy per inference. It can change humongously based on your spatial unrolling and your memory hierarchy. It has a very, very big impact. And you cannot see which spatial unrolling is the best, nor can you say which memory hierarchy is the best. It's very dependent on each other. What is the optimum? You have to co-optimize them. And moreover, if I would show you some more results, we would see that these optima, which unrolling and which memory hierarchy is the best, is very, very workload dependent. And also dependent on what precision you compute at, whether you compute at 1 bit or 2 bit or 5 bits or 16 bits and so on. So now we're in trouble, right? Because we thought we could optimize nicely at this level and someone else would optimize at this level and someone else optimizes here. But it starts to be very clear that this is all very influencing each other. It's all very intertwined. And let me illustrate this to you with a very practical example to show you how much impact it can have. I'm going to start with a chip that was designed in my lab. It's our Envision chip, published in 2017. It's a fully digital processor that has 8-bit processing elements, max, and it does an XK spatial unrolling, a certain parallelism in my data path here. About 80% of my power went to memory, about 20% of my power went to compute. It's very typical in digital processors. If you look at it like this, okay, if we want to optimize further, obviously what we could do is reduce the number of bits in our design and start to do 1-bit computations in a digital way, like I showed you a few slides ago. So it's a chip called Binary that we taped out in 2018. And what you see, of course, if I go to 1-bit computations, my memory power drops a lot because now I fetch 1-bit data instead of 8-bit data. And also, as we saw, the Mach power consumption drops humongously because 1-bit operations are very simple. But still, of course, I'm memory dominated because both shrink. To be honest, my Macs hardly take any space on my chip anymore because they're just 1-bit teeny tiny Macs. You could say by looking at this, okay, there is not much room for improvement anymore. Even if I go to analog or in-memory compute, it wouldn't matter much because this blue pie is so small that why would I optimize it further? To be honest, this is because we chose this data flow, which was good for digital, 8-bit, but this data flow is not very smart for my 1-bit processing. Because my Macs are so small, I don't have to stick with such a small number of Macs. I rather take a much larger number and a data flow is spatial unrolling across many more dimensions. We used 4 different spatial unrolling dimensions here to map, basically in the same or small chip area, 64,000 multiply accumulate units. The result is not that my Mach power or Mach energy consumption is less. I still do the same number of operations, so the blue part of my pie chart is the same size. But my memory access cost drops humongously now because my data reuse goes up. Every data element I fetch from memory, I now don't use 16 times, but I use thousands of times. So I'm basically reusing my data more, and my green part in the pie chart shrinks tremendously. Now, this is interesting because this opens up new opportunities for further circuit level optimization. Now the blue part is dominant. I can start to play again with my Mac, maybe go to analog compute. But I can only do this because I changed something at the architecture level in my data flow. Because I played with my data flow, I have new circuit level opportunities. So that's what we did. The same chip was taped out with exactly the same digital architecture memory hierarchy, but we replaced the digital Macs here by analog processing Macs. And what you see, the green pie chart stays the same. It's the same data flow. So my memory hierarchy consumes the same amount of power or energy. But the blue part, the digital compute, now becomes analog compute and shrinks almost by a factor of 10 or more than a factor of 10 in energy efficiency. Interesting, because my blue part is now almost gone, my green part is dominant again. I did a circuit level change, which now opens up new opportunities at the architecture level. Because now I can maybe again play more with data reuse and shrink down this green part further at the architecture level, which we're basically doing now with in-memory compute, a collaboration that I have with IMEC. I think the most important message from this is you have to co-optimize the circuit level and the architecture level. By changing something at one level, you open up optimization opportunities at the other level. You cannot think about them independently because you miss like orders of magnitude of efficiency savings. So it's pretty clear these left ones are very intertwined. And without having the time to go into a lot of depth, let's briefly look at this algorithmic level where there is also this very close linking with decisions I make at the other levels. And to understand that, we have to start from the observation or the common knowledge that I can design a neural network to do a certain task at 16 or 8-bit precision, but I can also design a network for the same task with the same task accuracy at a lower precision. But typically, I have to then make the network wider or deeper or a combination of both. You basically need a larger network to get the same accuracy for a certain task. And if I go to binary or ternary networks, again, I will be able to typically, at least with ternary, still get a solution that gets similar accuracy, but the network has to be much bigger again. A bit more quantified, these are results that we ran for Cypher 10. Every dot in the graph is a different neural network topology that gets a certain task accuracy, expressed as error rate on the task, for a certain number of operations per inference. This is the size of my network. And these are the Pareto fronts for 16-bit networks, 8-bit network, 4-bit, 2-bit networks, and binary networks. And what you clearly see here is to get a certain accuracy, you can either have a very small 8 or 16-bit network or a bigger 2-bit or an even bigger binary neural network. The question to the algorithmic guys or for the algorithmic guys will now be, what's the most efficient network? Do I rather have a small 8-bit network or a bigger 2-bit network or a huge 1-bit network? I don't know. From looking at this, there is no answer. The hardware guys have the same problem. They say, okay, but which one should we support? Should we make processors for 1-bit or for 8-bit? The point is, by just looking at one layer at a time, either this one or this one or this one, you cannot find the solution. It is not a problem that solves itself at a single layer. You have to co-optimize across the layers. The problem is obviously that there are so many options. You have so many degrees of freedom at every level. How to find the global optimum? Obviously, for this, you need a kind of cross-layer exploration framework and one that runs very, very efficiently across all these layers. Also, this is something we're working on together with many other people, obviously. And the core of such design exploration framework is basically a good cost model. A model which very quickly can estimate the application level energy per inference or per task, throughput of my inference and my task, and my chip cost, basically my area or cost of my chip. And it should estimate this from, on one hand, a certain neural network workload that you want to run. On the other hand, the hardware architecture on which you want to map the neural network, about the memory hierarchy, the processing array, specs, and so on. A mapping of how you want to map the workload on the hardware architecture. This boils down to what data will you store in which level of the memory, how do you unroll your loops on your spatial processing element array, and so on. And you need some technology information. How expensive are memory accesses? How much area do my processing elements take? And so on. If you have a tool that can take these inputs and in a fraction of some microseconds estimates the system level cost, then you're ready to start design space exploration. Because what you can then do is start to replace each of these fixed inputs here by some iterations, loops, basically to try to find the optimum given some of the other inputs. If you look around, you will see that quite a few of these design exploration tools start to appear. In our lab, we developed one, which we are working with a lot because it gives us a bigger mapping space or more freedom than other frameworks that exist. Our tool is called Zigzag, and you can use it yourself here from a Git. And I'll show you next what the benefits are of this tool compared to some others. Now, how would you want to use it? The most simple thing you can do is give a neural network workload, freeze a hardware architecture, and try to find the most efficient mapping of this workload on the architecture. And then you get plots like this. On the y-axis, I have my throughput in terms of utilization and how efficiently do I use my array. The higher, the better. On the x-axis, I have my energy efficiency. How much energy does it cost me to run a certain workload? Here it's AlexNet on a fixed architecture of the Iris chip. And of course, the lower, the better. So here's where I want to be. So we freeze the model, we freeze the architecture, we freeze the technology, and we want to find the most efficient mapping or compilation of the model on the architecture. Most tools are then going to try to do loop allocation of my different levels in my convolution loops to different memory hierarchy levels and spatial unrollings, but they do that for all loops together. And then you get all the red dots. It gets you a certain best energy throughput trade-off. In our tool, we can independently schedule inputs, weights, and outputs where they are allocated and stored. And then you get an extended blue design exploration phase with much more energy efficient solutions, or even for the max throughput, also some lower energy solutions. So a larger design space, which is a benefit of Zigzag, resulting in more efficient hardware mappings. Of course, that's all when you only play with the mapping. We don't have to stop here. You can also say that I don't know my hardware architecture yet. What would be the optimal hardware architecture to map this workload, or maybe this suite of neural networks on hardware, and maybe you have an area constraint? What would be the most efficient architecture that fits in 3 millimeters square to map this workload with the lowest energy or with the best throughput? And you will have to, or the tool would have to figure out whether it should give more area to processing array, or it should give more area to the memory hierarchy, and what the best topology for each of them is, and so on. So also that we can do with this tool, where you get plots like this, and you have a trade-off between energy consumption on one hand, area usage on the other hand, on the x-axis, and the colors are for the throughput. The brighter, the higher the throughput. It's clearly a trade-off between these three parameters. So it's a fixed neural network model that we now map with flexible mappings on flexible hardware architecture. And you can see, okay, I have 3 millimeters square of area. What's the solution that gives me the highest throughput or the lowest energy consumption? This would be the best throughput. Here would be the least energy consumption. Now, don't forget, every single dot here is a different hardware architecture with a different memory hierarchy, a different spatial unrolling, which means that every single dot here has to go through this complete mapping optimization you see here and computing all the blue and red dots. So the cost model you see here has to run millions and millions or billions of times to find plots like this. This is where it's extremely important that the cost model runs very fast, fraction of a microsecond, and that you have very efficient search heuristics to search more efficiently in this space, because exhaustive search is simply impossible. Also, that is all built into the Zigzag framework we developed. Once you can iterate across this level and this level, you could even play with different technologies and answer questions like, what happens if I plug in a different type of memory cell? What happens if I have 3D interconnectivity instead of 2D? And so on. So these are explorations we're doing together with the Design Center or Research Center, IMEC. And then the final thing I want to discuss with you, because then I'll run out of time, is that you not necessarily only have to explore towards the bottom, the hardware and the technology, but you can also explore towards the top. I can play or put my neural network topology, the algorithmic topology, in the loop as well. Or maybe I have an accuracy constraint. I want to get 90% accuracy and give me the best neural network model and the best mapping to have the lowest energy or the lowest throughput mapping of this task on a specific hardware, specific chip. This is basically the domain of neural architecture search, but where neural architecture search nowadays still often uses very abstract cost metrics for your cost of your model, you can in this way make it truly hardware aware, where you're actually going to look for the neural network that has the lowest cost or the highest throughput or the lowest energy consumption when you map it on your custom hardware chip. And this brings us back to the example I gave in the middle of my presentation, where I have this very big 1-bit network or a smaller 2-bit network or an even smaller 8-bit network and so on. And you want to know what's now the most energy efficient system level memory topology, model topology. And again, with the cost model you see here, you could do this because for each of the dots in the graph here, I could assess the throughput on hardware or the energy consumption they have in specific hardware architectures and get a graph like this. Right now I have the accuracy on the x-axis, my system level energy consumption on the y-axis, and I can totally pick out the architecture, the model topology that gives me the best energy consumption to reach a certain accuracy, and reach a certain task level accuracy. And in this case, a 4-bit implementation was the most energy efficient after all. By the way, this is very, very workload dependent. It's not true that for any different type of application, 4-bit is the best. It's exactly where you need such a co-exploration, a cross-level exploration for. So in summary, many trends are happening at each of these levels in isolation. But the main message is, if you're working at one of these levels, don't be basically don't keep staring at your own performance level, pushing the tops per watt or ops per inference and so on. Stop bragging about performance metrics at each of these levels, because the only thing that matters at the end to the user of the platform is how much energy does it cost me to do an inference, how much time does it cost me to do an inference. And if you optimize something at one layer, you better make sure it doesn't make things worse at the other levels. Or if you change things at one level, you can see what new opportunities open up at the lower or upper levels. And definitely you need a good cross-layer framework to explore these interdependencies very quickly and try out big design space of all the options you have, where Zigzag can offer a solution. This brings me to the end of my talk. I will leave this window open with some references that I use for people that want to dig deeper, and I'm open to answer some more questions if time permits. And otherwise, you can always email me, because let me go back here, email me or contact me for any follow-up discussions. Thank you for your interest.